So this is the second of the two lectures. We will try to do classification or machine learning. We will do three different models. We will explore decision tree, k-nearest neighbors, and logistic regression. I have example for that we will try to solve by these three models. Example that we'll try to solve is fairly maybe silly. So I have an animal and I managed to measure the weight and I managed to measure the claws. And I would like to know if it is a cat or a dog. Right? The weight and the claw, those are just made up numbers. They don't mean anything. I don't know what the units are, so you can make whatever units you feel are fun, right? So, and I observed several cats and dogs, measured their weight and claw, and here I have a table. It has several cats data, several dog data, and I would like to know the animal that I measured for weight and claw. Is it a dog or a cat? Can you tell me? Right? I have an animal and I check what its weight. It's 135, and what is the length of the claw? It's 3.5. Notice there are no units with it. It's just random numbers for the entertainment, so we have some data project. Right. So is it animal dog or a cat? What we'll try to do is we will try to look at the different animals, cats and dogs. Here are the animals, cats and dogs. I have 4 cats and 3 dogs, and for each of them I measured what's the weight and what's the claw, and then I have this data. Right? So first thing, we put it into data frame. You can look at it, data frame. Here it is. Right? Here are the basic imports where we import panda. We will do pictures, so plotlib and seaborn, and we will need some numerical tools from NumPy. Table is good for computer but terrible for humans. Here is a plot of the data. I plotted the entries for cats and plotted the entries for dogs, and then the red dot is the unknown animal, and we have to decide if it is a dog or if it is a cat. Right? Here you are eyeballing it. It's not quite clear. See how it looks like. Looking at table is great. Looking at the plot is much better. So we have a bunch of points. So I will do a scatter plot. And data is my data frame, and then what is on the x-axis? Weight. What is on the y-axis? Is the claw. Oh, and here it is. Each point represents one point in the data. Maybe it would be nice if we distinguish them by color. So U is animal. Alright, so now I have cats and dogs. Okay, and now I would like to know also where is the unknown one. So I can here plot just one point. Plot 135 was the weight, 3.5 was the claw. I want a dot, it is red, and let's see, here is the red dot. Maybe cool if the legend shows what it is. We say label unknown. Right? It depends how you like. You can also make it like a X that is green. Right? So this is the unknown point. We are trying to figure out if it is a dog or a cat. And here is a redrawing to make it easier to see. So there are the dogs at the dog spots and the cats at the cat spots. Right? It's kind of close to a dog, but at the same time it's in a cluster of cats. Yeah. First thing is decision tree. Okay? I will try to make a series of questions such that at the end it will tell us if we have a dog or a cat. Right? So first we look at all the animals. We ask the animals, what is the claw? Is it at most 3.5? And if the answer is yes, we go to one side. If the answer is no, we go to the other side. Right? So if the answer is yes, I think we go to the right. We go to the right. And if the answer is no, we go to the left. Right? And if you go to the right, then there are 3 cats that have the claw size bigger than 3.5, so that's the note on the right, and we can say it is a cat. And if the claw is less than 3.5, then we look at the weight, and if it is less than 130 or not, if it is less than 130, then here we go to the left, and we have the cat, and if it is no, it's bigger, then we go to the right and have the dog. Right? So what is in the notes? So first is the condition that you check. Yes, no, yes goes to the left, no goes to the right. Then there is a Gini. That is some measure of how much uncertainty there is. Right? We will get to it carefully in a little bit. Samples is how many samples we need to classify, and value is what is the split between cats and dogs. So if the value says 4-3, it means there are 4 cats and 3 dogs, and samples is 7. That's how we start. And then after the first question, if we have claw less than 3.5, then 4 of the 7 animals satisfy that. 1 is cat, 3 are dogs. And if the claw is bigger than 3.5, then we have 3 samples left, and all of them are cats, none of them are dogs. Okay? And in this decision tree, if you go, whenever you get to the value that has one of the entries 0, it's clear that it must be a dog or a cat. Right? And if you have an unknown animal that you want to test, you start at the top, you ask the questions that are in the first line of the notes, and as you go down, you are getting closer and closer to being either a cat or dog, perhaps, and you are in the at the bottom, where the value is a list that contains only one non-zero, then you are sure that it's a cat or dog based on this classification. Okay? The Gini is a number that the bigger it is, the higher from sure is the result. Right? It's not exactly, but something like that. So you want to have the Gini, it's called Gini impurity, you want to have it as small as possible. If you want to implement this in Python, in a scalar, it's fairly simple. You import the model, the classifier, you prepare the values x and y, and you ask fit, and that will create this decision tree for you. Right? And you don't have to do any decisions. Decision tree classifier. So I'll need to import the class that will do everything. So from scalar.3 import decision 3 classifier. Right. Okay, I have the classifier imported. Now I have to make the x and y. Remember, we have this data frame that has weight, claw, and animal. So what I can do is features. Okay, make a list of the features. Features are the weight and claw. It's the features because those are the thing I know, and not the thing I want to predict. So x is the data frame features. And if I do it like this, then x is only the weight and claw. Right. Y is the label df animal. Yeah, y is the series with animal. Good. Right. Now I will make instance of the classifier CLF decision 3 classifier. If I have more of them, I can put them into different variables. Okay, so CLF decision 3 classifier. I will create the classifier. I'll fit the data in it. So fit x values. So I don't have problems with the names later. Oh, and I have the classifier. Now the tree is ready, and I can try to classify what is the surprise animal. It's in parentheses. Now I write the it's a list of possible entries, and I write the 135 was the weight, 3.5 was the claw, and tada, dog. Alright, so prediction is that we are getting a dog. Right? Decision 3 will try to visualize it, so you see how it looks. So from scalar import 3, and there is a function that does all the drawing for you. So 3 dot plot 3, and CLF was the classifier that had the decision 3 in it. Bam! Look at it. Here is the tree. Here's some I know what x0 is, x1 is. Those are the entries in the x, and the first and 0 was the claw and weight. If you want to make it a little bit easier, you write feature names equal. We had variable features, if you remember, and now it says claw at most 3.5, weight at most 130, so now it's easier to read. Right? Here is saying value 1003, it's the number of cats and dogs. If you want, you can also add class names, and you say first where the cats, saying cat and dog. I think I put too many parentheses. Right, see, and now it writes cat because there are more cats. Here it is dog, there are more dogs. Now in the leaf it tells you if you end up in this leaf you are as a cat, here you are a cat, you are a dog. Right? Other things you can edit, like if you want rounded corners, you can edit rounded corners. And, I maybe now it has rounded corners. Well, let's look at the Gini impurity thing. It was after Italian mathematician. Right. I have 4 cats and 3 dogs. Right? If I have no other idea about any of the features, how can you make classifier that is reasonably classifying the 4 cats and 3 dogs. So you will maybe say, oh, I have 7 samples and 4 of them are cats and 3 of them are dogs. So if you ask me what animal do I have, in 4 out of the 7 cases I answer cat, and in 3 of the 7 cases I answer a dog, right? So I am making this classifier that is fairly straightforward, that you ask me, is it a cat or dog? And I say this in 4 out of 7 cases I say cat, and or with chance 4 over 7 I say cat, and with chance 3 over 7 I say dog. Right? I didn't look at any features of the data other than how many are there, how many entries are there. Right? So this is a random classifier. Right? And question is, how often is the classification correct and how often time it is incorrect, right? And the incorrect thing is the Gini impurity. If you look at the tree on the right, if you have only entries that are of one of the 2 cats or dogs, if you only have cats in your data in the particular node, then you always answer cat and it will be always correct. So the incorrectness is 0. Okay? So kind of you can think of the Gini as incorrectness of a random guess, where the random is weighted by how many things you still have. For the first node, if you want to make the random classifier answering cat with chance 4 over 7 and dog with 3 over 7, and you try to do it on the 4 cats and 3 dogs, you will be correct in 51% of the questions. So there is the little calculation. I'll try to show how it goes. So here it is written as the formula: 4 over 7 squared plus 3 over 7 squared. Alright, so let's look at it. Here's a calculation for the correct classification. So expectation for the correct classification, you can think of it that what's the chance that you have a cat in 4 of the 7 cases you have a cat, and what's the chance that you answer correctly if you chose a cat, right? You are answering cat with probability 4 over 7, so it's 4 over 7 times 4 over 7 is the first part. And then what's the chance that you have a dog? It's 3 over 7. And what's the chance that the answer is correct? If you have a dog, you answer dog with chance 3 over 7, so you will get the correct answer with probability 3 over 7. If you evaluate this, you get 0.51. And chance of incorrect answer is 1 minus chance of correct answer. But this good to remember. If you have a high Gini, that's bad. Low Gini, then it's good. So you want to have a low Gini. If you have 4 cats and 3 dogs, 2 classes, that's what we did before. And if you have more of them, then you could try to say that you have a PC probability that random sample is a cat, number of cats divided by the total number of samples you have, and PD probability that you have a dog, which is the number of dogs over the total number of samples, right? So you have 1 minus PC square minus PD square is the Gini impurity. If you have k classes, we have more classes, then it is 1 minus some over all pi squares, where pi is the probability that random sample is coming from class I. What you want to do when you do the decision tree, you would like to always make a split such that the Gini impurity is decreasing as much as possible, because then it makes it closer and closer to things where you can classify perfectly. Oh, here's more details. So we start at the top node if we want to make a decision tree, and then we look at every feature and value for the feature, and try to find a best split. Right? The best pick is minimizing the Gini of the resulting nodes. Right? It is you can try to say that there is a lot to choose from if you have many features, and then the features have real values. But yeah, that's what one needs to do. And then when you have the new nodes, you can split them and you can keep going. Sometimes question is, when do you stop doing this splitting? Often the splitting doesn't happen all the way until the very bottom, but sometimes the split is good enough that maybe it's better to have a smaller tree than a tree that in the end wiggles a lot. So in practice, often we stop before having Gini 0. Here the decision tree was small enough, so the Gini 0 actually happened. But there are two reasonable stopping conditions. You can stop at the maximum depth, so you say, I will go to depth at most blah, and then it will stop. Or when the Gini is small enough. Right? What may happen is that you have some outliers in the data. Right? And if you get to a box where you have there 20 cats and 1 dog, maybe the dog is a real weird dog, or maybe the dog was a mislabeled cat, and you may not want to try to carve out a little spot there for a dog. You just say, yeah, whatever is here is cat, right? And you maybe accept some error rate for that. So it's a thing to keep in mind, that if you don't go all the way to that bottom, sometimes it helps eliminate some weird outliers, and you will also possibly get a nicer line separating the different categories. Try to see how is our classifier working. Here I'll copy paste what we had before, and that is the plot where we have the dogs, cats, and the unknown point. What I would like to do now is try to display for every point that is in this plane whether it is classified as a dog or cat, right? Maybe this is not the only unknown point. Maybe every point could be interesting for us. Right. So what we will do is that we will try to create a lot of data points like these unknown ones, and for each of them we will try to ask the classifier to decide if it is cat or dog and plot the result. Right, so comment this out for a little bit. We'll get back to it in a little bit. So first I need to know what is the minimum and maximum for each axis. Right? So I have the x, so let's say I have the weight, and take the minimum of it. Minimum of the weight, that would be the minimum on the x-axis, so x min. I'll say here -1, so we are 1 away. Alright, now I do the same for maximum, min, max. Maximum I add 1, so now I have points that I will be for weight 1 less, 1 more, and I will do the same thing for the other axis. so it's a claw, right? Y min y max. Right. Now I need to generate a lot of points between y min and y max. For that we will use numpy. Okay, use np.arrange, and it will say from which xmin, xmax, and the steps. Too many r's. Okay, so now we have list. List. So bunch of floats. It goes from xmin to xmax. Let's see how they go. Right. Maybe I went too far. Right. So this is for the x, and then I will do it also for y. Y min y. And I would like to have a two-dimensional thing out of it. So np dot mesh gate. So, oh, and it gives me a bunch of arrays of coordinates. You can split it into xx and yy. So I have x coordinates and y coordinates. For the first blob I have x coordinates, for the second one x coordinates, for next one x coordinates, and then there are the y coordinates. First is y0, then there is y1, right? Does it make sense that for the y coordinates the lists are always constant but slowly increasing? For the x coordinates every time the list is increasing, but the list repeats over and over. Alright, if I want to make it into one long array, then I do revel, and now it is a one big long array. Alright, I have a bunch of xx, that will be the revel, and here is the y's coordinate that corresponds to it. So now there are two lists of x's and y's, and I can try to predict what is the value for these x's and y's, right? So my classifier CLF predict. We will use predict proba, which doesn't really help us right now, but in the other ones it will. If we perhaps did not have the decision tree complete, but we cut it off earlier, then it will give us a probability that something is a dog or a cat rather than just 0, 1. And P, now we combine this xx dot revel and yy dot revel. Okay, maybe we can try to call this and now it gave us prediction z equals, and now I need to reshape it. I need to take everything but only the other coordinates. Maybe let's try it. These are the predicted numbers, and reshape it same way as x is dogs cats, and see this is my z. Alright. And now we can plot it. Plot contour F, and I put the X coordinates, Y coordinates, Z coordinates, and C map, color map, let's say let's type palette, color map, and greens. And the more green it is, the more dark it is. Right? So this is a color palette for it. I can try to put this back. And here you go. You see the dogs, the unknown one, here are the cats. Right? You can add different palettes if you like. Maybe the one that is in the slides is red, yellow, blue, blue. These are cats, and this is dog. Here you will see the transition better. Here it's a little bit more smooth. Alright, so this is how you can plot what happens in the classifier in a little bit more visual way. K-nearest neighbor is another classification algorithm, and it is based on the following simple idea. You show me your friends and I tell you who you are. Right? You look who are the other data points that are near, and when you have the data points that are near, that's how you decide what's the class of the unknown one. So here it is. I have the red dot and the k nearest neighbors. K is a variable that you can change. Right? So if you say I will classify the red dot by the first nearest neighbor, then the first nearest neighbor is a dog. So you would say the red dot that I measured is a dog. Or you can say, oh, let's look at three nearest neighbors. So I look at the three nearest neighbors. The three nearest neighbor is one dog and two cats. And then cats has a majority, so we would classify it as a cat. Right? Here we are experiencing something that it is not obvious what the answer should be, and it is not immediately correct to say that the red dot is dog, and it's not immediately correct to say it is a cat. It just, the data are ambiguous, and based on your classifier you may go either way. Right? Based on the k, the number changes. If you have two options for your outcome, cat or dog, then having two neighbors may be bad, because if you have two neighbors, then you would have the nearest two neighbors would be cat and dog, and then you do what? Right? You so that's why there is 1 and 3, so you have an odd number, so you always have a majority. Applying this in the Python is again very straightforward. You say I want a k neighbors classifier, you write the k there as a par argument, and then you fit the data, and you can call predict, and it will tell you if it is a cat or a dog. Neighbors classifier. So first, from sklearn I have to import the classifier. So from sklearn.neighbors import k neighbors classifier. Right. see, so now I have the classifier imported. I can create it. CLF is can neighbors classifier, and we put there maybe one. What's the one nearest neighbor, right? Classifier dot fit. And we put there the x values that we prepared before and y. All right, so life is good. We have it. Fit it. Now we test what's the answer. Classifier dot predict, and we predict the one entry, and the one entry is 135 width and 3.5 claw. Alright, so the nearest neighbor a classifier said it's a dog. Right? You have 2 nearest neighbors, it's cat, 3 nearest neighbor, cat, 4 nearest neighbor, cat. Right? What you can do is here write predict proba, and now it will tell you what's the chance of it being cat or a dog. It looks at the 5 or 4 nearest neighbor, 3 of them are cats, 1 of them is dog, so 75% chance of one and 25% chance of the other. Right? So 50-50, it's 1, it's 0 cat, 1 dog. Right? So here you can get either the number that is rounded to this is the largest, or the one. You can see both of it, depends on what you want. Now I have my classifier for the k nearest neighbors, and I would like to make a plot how it looks, right, for all the other numbers and other values in the plane. So we will use the same trick as we did before. We already have this variables xx that we created before, and yy that are dense coordinates all around the 2-dimensional plane. So I will do I will take the classifier, do predict proba, change the probabilities, and p c, and here is we will do the x coordinates as one list, y coordinates as a long list. Okay, and we'll save this into z. Okay, z. These are the 0, 1s, 1, 0 based on whether it is a cat or a dog. So what we'll do is we only keep when it's a dog. So now it's an array of dogs, and what's the chance of dog being there, and then reshape it to have the same shape as x, the 2D array, great, and that's what I will call z. And before okay, now I'll move this around, calculate this first, and I will plot the contour, plot contour f, float, x coordinates, y coordinates, now z has the same shape, color map, maybe greens. Okay, so now every point here is the more green, the more likely it is a dog. Right? Here, definitely dog, less likely to be dog. Right? So let's see, the neighbor classifier 1/2. So at the red point it is 1/2. So this is half and half. This is dog. This is cat. Right? and then if you change the classifier, how many neighbors you see, then the map also changes. Now it looks like this: cat, dog, cat, dog. So you can play with this and have more and more different pictures. Nearest neighbor, and if we plot the classifier, how it looks like, we get this picture. And now it may look kind of weird, right? Because I am saying that the green, dark green, the nearest neighbors are dogs, and the nearest neighbors are cats, right? But if you look at this point over here, it is much closer to the cat than to the dog on the screen, right? So what's wrong? What went wrong? So the point is only 1/2 away in this way, or over here it's maybe distance 1.5, but in this distance it is about 5, right? So the scale of weight and claw is very different. Okay? If you want to have it better scaled, then you can get the current axis, get current axis, and you can set the aspect ratio. Set aspect equal. And now it looks more like it, right? Now the points are really closest to the here are dogs that are closest to the dog, here are cats closest to the cats. Okay? If you want to make a bigger picture, you can also change the x, y points that you sample. I'll copy what we had before to define x and y. So this was the definition of x and y. And if we increase the y min, y max, let's say +10, -10, we'll get a little bit more space on the y-axis, and maybe you'll see. Right? So now you can see how the classifier classifies what is cat, what is dog. So this is what the k-nearest neighbors does. So it's non-linear classifier, like the classification is a little bit like this, wiggled around. Okay. This thing that it gave slightly weird results when the aspect is not equal, and one would like to say, hey, in the claw coordinates, the distance 1 is means something different than for the distance in weight, right? And for that there will be some standard scalar where we will apply it to pre-process the data. So that's for future class. Okay. Here is a quiz question. So for k equals 3 and 4, if k is equal to 3 or 1, 4, and I have the green thing, it's a question mark, and I would like to classify it. Is the green circle, should it be a blue square or a red triangle? Right? So if I have k equals 3, then it would be classified by k nearest neighbor as triangle, because there are majority of triangles. Right? If I have k equals 5, then it would be by the dashed circle, and the dashed circle there are more blue squares than red triangles, so we would classify it as blue square. If you have k equal 1, then you just take the nearest thing. So we would classify it as a red triangle. If you have k equals 4, then you cannot say, because there are two blue squares that are near and two red triangles. So yeah, the classifier is cannot determine if the green circle is more like a triangle or more like a square. Next thing, classifier is a logistic regression. What it is trying to do is separate the data by a line. It tries to put a line and put the cats on one side of the line and the dogs on the other side of the line. And then the unknown point will be on one side of the line, either with cats or with dogs, and that's how you classify. In this case, if you would have a line separating the data like this, the red unknown animal would be classified as a cat. Here one has to be careful. We'll see that separating the data by a line is not always possible. Right. So here, to make the example first, we will switch from 2D to 1D. So let's say we forget one of the coordinates. We forget about the claw. Right? The only thing that we have now is the weight. Right? And on the that's on the x-axis, and on the y-axis is whether this animal is dog or not. Right? Instead of 2D, we just do 1D because it will show a little bit better what is happening. Right? So how does the classification looks like? Right? And then the unknown point is somewhere there in the middle. Right. So what we try to do here is put a S-shaped squiggle here. Right? We hope that the cats are more to the left, the dogs are more to the right. So I would like to have this squiggle here that will tell me how likely the outcome is a dog. Right? And if the weight is large, it should be large, close to 1, and if the weight is small, then I would like the outcome to be 0 or close to 0, which is not likely to be a dog. Right? Right. And so here's a little formula. So for each weight S, to tell the probability it's dog, the P of X, the probability of weight X that is a dog, is 1 over, and in the denominator there is 1 plus e to the minus x is the variable, the weight, minus u over s. Okay, and the u and s are parameters that you can move around, and as you move them around, the s-shaped curve changes. Right? So for the u parameter, it moves it left and right, and the s makes it tighter or less tight. Create the S-curve for the logistic regression. Right, so I will try to do first plot and then we'll put things in it. So I will figure axis, I have a plot, equals, it does nothing quite yet, but I'll put things in it. So I will put a scatter plot in it, x dot scatter, and on the x coordinates I will put x, but wait, and on the y coordinates we will put y dog. So this will be a let's try it. What is y equal dog? Okay. it will be true, false, 0, 1 thing. So for cat it will be 0, for dog it will be 1, and color red. Okay, so now we have, here are the weight for the cats, and here is the dogs, 3 dogs, right? Right, and now I would like to try to plot here the function p of x, that is 1 over 1 minus exponential of minus x minus u over s, right? So I'll do it that we will take a lot of small pieces, small points that go from 120 to 150, like this, x and p dot length space from 2, and how many points you want between. Now we have a bunch of points, and we will let's call it xs. We will pick u, some number, and we pick s, some number, right? U is the center and s is how shifted around is it, so it's around here. So we can do ax dot plot, and I would like to plot here xs for the first coordinate, and for the y coordinate you will do this thing, 1 over 1 plus numpy dot x, and here is minus xs minus u, now I don't see it, minus u over s, right? And this is the line that is saying what's the chance that animal with a given weight is a dog. So here the chance is 0, and then it increases, and now the chance is 1. Okay. Right. It would be nice to see different values for s and u. Right. So let's copy this front. It was for the one axis. Oops. Comment it out. We don't want to show it again. This is showing one case of S curve. Right. So here I will do it by plotting several of them. Okay? And I will do it with a for loop. For S in, I'll put there several different 0 0.1, 0 0.5, 1, 5, 10. So we see how the things changes. We will plot them. Right? And now we have a bunch of them. It would be nice if we have some chance of seeing which one is which. So we can write here label is S. We have them labeled. We also should perhaps show the labels. Legend, legend, title. We know what is it. S. Okay. Now a few other things you can add frame on if you don't want the frame there. Okay, so now this is a large, this is the 5, this is the 10, this is 1. So as you are making a smaller, it looks more like a step function. Okay, this is a variation of S. We'll do also variation of u, variation U. I'll comment this out. So I will vary U, maybe 130, 140, 150, string perhaps U, title U, up. Okay, now you see that as the U is changing, it moves the S curve left and right. So how can you tell if the S-shaped curve is good or not? I have some data, xk and yk, they are over on the right. So you can see, right? And what I would like is that if the answer is 1, then I would like to have pk to be large, and if answer is 0, then I would like to have pk small, right? So here it is. For every xk, I will evaluate the pk. I will evaluate what is the curve for given u and s telling me, and then for the ones that should be 1 for the dogs in this case, I take pk's and multiply them. It is the p4 times p times p6. And for those that should be 0, I take 1 minus. So here is 1 minus p0 times 1 minus p3. So in each instance, if the classification was good, then the number is high, right? So either p4 is high if the classification as dog was correct, high, or if I classified correctly, then I get let's say p0 close to 0, and 1 minus close to 0 is close to 1, right? So what we would like to do is find u and s such that L is maximized. The maximization of L is right, our goal, and u and s are two things that we can move around. U moves around the center, and S moves around how stretched out the S is. Okay. Problem a little bit is that maximizing a product is hard. Right? Yes, you have a polynomial of a high degree. So instead of maximizing product, you would like to maximize sum. So the way how you can turn a product into sum is to take natural logarithm. So here we take a natural logarithm, and then we can maximize sum. We do it because it is numerically more stable to maximize sum instead of product. So here it is in 2D, right? Remember I think we are separating by line. So what we are actually getting, in a way, is not really a line. Right? We had the squiggly thing in the one-dimensional case. So what happens if we have the two-dimensional case? Do the logistic regression classifier. So I will import the model, linear model, from import logistic regression. Right. Okay, let's see. Okay, create the classifier. Maybe made the same typos twice. Right. I will fit the data in it. The values. This is the part where the U and S are optimized, and now we ask for the prediction. 135, 3.5. Right, and we are getting as a prediction cat. Here again works the thing that you can do predict proba, and you will get what's the chance of seeing a cat. Okay, here's comma. So 66% chance that we are seeing a cat. Right. Right. So those are the two options. Right. Let's try to plot the thing. This is the, I copy pasted the contour thing that we had before. We create the grid and try to predict things. So here is the contour for it. Right. Maybe let me try to find also the cats and dogs. So we can put them in so as this little piece. So now you see where are the dogs and where are the cats, and how this more green, more dog, and then as you get less green, less dog, right? And you see how there is the line. It's kind of a wave in 3D, more like, right? Slightly unsatisfying is that there is now the S function is smooth. It's not like this. So what you can do is change and draw it as an image palette, image show Z, and we have to write here a little bit x min, x max. Where are we drawing it? Max, origin lower. Should probably comment this thing out. Color map. Keep this one. Aspect auto. Right. And now you see it's a little smoother transition. More green, more like dog, less green, less like dog. Sometimes if you feel it's too dark, you can have here alpha 0.8. Sometimes people like it. It gets a little bit less intense. You can still see. If you want to see what is the line that separates things around 1/2, you can look at coefficients, give you the slopes, and then color for that intercept. And you can use this if you want to draw the line that separates cats and dogs. But you can look at it in a code that is below. I think it's best to draw it in a maybe 3D, or one should draw it with some kind of a weight, right? So you get for each point in the weight coordinate system, you get how likely it is to be a cat or a dog. So you get a value between 0 and 1, or how likely is it to be a dog, right? And when the color is blue of the background, it is likely to be a dog. And if the color is red, then it's likely to be a cat. Here in this picture, the red and blue are slightly shifted. right? And this you can see as a 3D that you have it as some kind of like surface in 3D that at the places where we have a lot of dogs, it's close to 1, you can see it on the right, and in the places where we have cats, it's close to 0. So you have like this 3-dimensional shape actually, right? And the line is where this surface is equal to 1/2, right? This is a similar thing if you try to do decision tree. You can try to make the decision tree and also plot it and see for every weight and claw how it would classify each point, right? And if you plot it as a surface, you can see it's like a big jump over there. Either it's 1 or 0, right? So this is our decision tree, how it performed. And this is how one nearest neighbor looks like, how to classify cats and dogs. Neighbors for cats and dogs. You can notice that there is a chance of being dog or cat. You can have it 0 or 1, or also somewhere in the middle there is a strip that is saying about 1/3. So chances 1/3 of a dog. So it tells you 2 out of 3 in the nearest, in the range over there are cats. Right? So the if you have k nearest neighbors, it can give you a probability of being a dog instead of just being a dog, yes, no. So in our case that we had, the logistic regression seems to work fine because there is kind of separation by a line of the data. But if the data would look like this, then the logistic regression would be quite bad, right? It's kind of at least visually clear that there is some separation between the cats and dogs, that if you have a more complicated shape, you would be able to distinguish cats and dogs. But simply cutting it by a line will not do it, right? So don't rely on saying I apply logistic regression and life will be great. Sometimes yes, but sometimes you have to use a little bit more complicated things, right? Right. Next time what we will try to do is figure out when the models are doing well or not, and that we will do with train test split, some k-fold validation. We will look at confusion matrix and ROC curve. And then we will try to explore standard scalar, which is making sure that the unit that we put in at one unit doesn't completely dominate everything else. So here's a cheat sheet for machine learning, right? So you start, you look if you have samples. If you have not enough samples, you should get more data, or things you are doing will be too unreliable. Then you look if you are predicting a category. Either you are predicting a category, cat or dog, or you are predicting a number, predicting a quantity, right? And if you are have labeled data, which means you are predicting cats or dogs or whatever, then you try to use classification. And then you can see there the k nearest neighbors, there is some bias, there is some support vector machine, which we will touch on later. Or you do not have labeled data and then you are trying to find some clusters, you will try clustering later. Or if you have quantity, then you can try to do some regression, linear regression, which we tried. Or if you have data that are too big, you can try to do some dimension reduction, some PCA, which we will also try later. The decision tree, k nearest neighbors, and logistic regression, all of them are covered by StatQuest. Highly recommend. It should give you some idea how these work a little bit more under the hood.